All right, now we are going to talk about consensus models. So a key aspect of blockchain technology is determining which user publishes the next block. Note that if there were ever two valid chains presented to a full node, the default mechanism in most blockchain networks is that the longer chain is viewed as the correct one and will be adopted. This is because it has had the most amount of work put into it. So that is the whole idea. So assume that at similar times, two valid blocks are found. For instance, in Bitcoin, two different people solved the cryptographic puzzle. So they provided two different solutions. So for instance, let's say that this is block number 1000. So there will be two different blocks with the number 1000. So some part of the network will think that one of them is valid and the remaining part will be the other one is valid. So this creates a conflict. So actually you wait a little bit and one of the blocks actually receive the next block. So some people solve the puzzle and obtain the block number 1001. And the whole network now sees that it is longer than the other one. So people abandon this and move on to the longer block. So this actually, in Bitcoin terminology, the one that is abandoned is called orphaned block. So people who solve that puzzle actually doesn't gain any reward. So actually you spend your resources for no reward. But in Ethereum, actually, those blocks called uncle blocks, and you receive reward for that too. So for the person who solved the puzzle and the block that is included in the real Ethereum blockchain receives currently 2 Ethereums, but the person who found an uncle block receives 1.5 Ethereum. So it is a different approach. So how the consensus model works. So the initial state of the system is agreed upon, the genesis block. So for the Bitcoin, the genesis block was created by Satoshi. So it is hard-coded in the Bitcoin core implementation. So you cannot change it. Users agree to the consensus model. For instance, in the Bitcoin, again, the model is determined by Satoshi. Every block is linked to the previous block by including the previous block header's hash digest. Users can verify every block independently. So anybody can verify it just by using the public keys of the people. So software handles everything and users do not need to be aware of these details. So that is the good thing. So you don't need to care if anything is wrong or is correct. Most of the time you are on the correct blockchain, and maybe a conflict occurs, so you are maybe in the wrong blockchain. So maybe a transaction that looks like it is included in the blockchain might not be included in the original blockchain. So for this reason, people generally wait a little bit more to see if the block is really included in the real blockchain. So most of the time when a transaction occurs, people wait for a bit more blocks to append to the end of this blockchain to be sure that that transaction is really happened. So in Bitcoin, the current agreement is to wait like 6 blocks. So people also don't know this, but whenever actually you pay for something, okay, it happens in 10 minutes, but people also wait 6 more blocks, which is 60 minutes, an hour, to be sure that it is really included in the blockchain. This is important because people think that they can use Bitcoin as a real money, you know, pay for your pizza and leave, or pay for your beer at the bar. But actually, when you pay it, the other person has to wait for an hour to be sure that you really paid for it. So you have to wait there for an hour. If it doesn't include it in the blockchain, you have to pay it again and so on. So this is why you cannot think of Bitcoin like a real world money, because nobody would wait for an hour at the supermarket when they buy something, right? For permissionless blockchain networks, the consensus model must work even in the presence of possibly malicious users, since these users might attempt to disrupt or take over the blockchain. Note that for permission blockchain networks, legal remedies may be used if a user acts maliciously. So this is the good thing. So in the permissionless networks, we don't know anybody. So people might try to take over. So if they have more than 50% of power, they can actually take over the blockchain. For the permission blockchains, since there are some real world identities or used because there's an authority and so on, you can take legal action if somebody acts maliciously. A key aspect of blockchain technology, again, is determining which user publishes the next block. And there are many consensus models. Most famous is the proof of work, where you actually prove that you are really trying to solve the cryptographic puzzle. This is used in Bitcoin, Ethereum, and for some reason, people think that Ethereum uses proof of stake, because years ago, they said that they want to change it to proof of stake, but they didn't. Ethereum also uses proof of work, and proof of stake is somewhat different. I will give more details, but it has many different versions. Other consensus models like round robin, proof of authority or proof of identity, proof of elapsed time, proof of storage, which is recently researched a lot. But there are also other things that I haven't included here. People come up with new consensus models. But most of the cryptocurrencies use proof of work. Some of them use proof of stake. So let's look at proof of work consensus model, shortened as POV. In this case, a user publishes the next block by being the first to solve a computationally intensive puzzle, most of the time finding a hash value which is less than a target value. The solution to this puzzle is the proof that they have performed the work. The puzzle is designed such that solving the puzzle is difficult, but checking that a solution is valid is very easy. So this is important. Versus in the Bitcoin, in general, the whole participating miners has to work around 10 minutes to solve it, but we can just take the hash of the block and check if it is valid or not, which takes microseconds. So this is very important. This enables all other full nodes to easily validate any proposed next blocks, and any proposed block that did not satisfy the puzzle would be rejected. A common puzzle method is to require that the hash digest of a block header to be less than a target value. For example, in Bitcoin, which uses the proof of work model, adjust the puzzle difficulty every 2016 blocks to influence the block publication rate to be around once every 10 minutes. So our aim is to have a Bitcoin block in every 10 minutes. So assume that we have a difficulty target. So really it takes around 10 minutes to solve this puzzle. But assume that everybody bought hardware, and assume that now the world hashing power is doubled. So we will start to find blocks in 5 minutes instead of 10 minutes. So most of the blocks now will be created in 5 minutes. But once we mine 2016 blocks, actually, this actually in average equals to 2 weeks. So the software just looks at how many minutes did it take to find these 2016 blocks. So if all of them are really found in 10 minutes, the difficulty does not change. But if we found all of them in 5 minutes, now the software actually doubles the difficulty problem. So this time, with this new computational power of the word, it will again take 10 minutes. So this 10 minutes was a choice by Satoshi, and in some cryptocurrencies, this is even smaller. In Ethereum, it is currently 15 seconds, but can change to 45 because there was a proposal like that, but maybe it changed, I'm not sure, but as far as I know, currently it is 15 seconds. In some cryptocurrencies, it is 2 minutes and so on. So the other one is proof of stake consensus model. This is based on the idea that the more stake a user has invested into the system, the more likely they will want the system to succeed, and the less likely they will want to subvert it. Stake is often an amount of cryptocurrency that the blockchain network user has invested into the system through various means, such as by locking it via a special transaction type, or by sending it to a specific address, or holding it within a special wallet software, and so on. So you're actually putting a stake there. Once staked, the cryptocurrency is generally no longer able to be spent. So this actually depends how you use the proof of stake. In some scenarios, actually it can be spent instantly. In some scenarios, it can be spent, but after some amount of time. And actually, I believe that this should be the case. If you allow them to be spendable at any time, then it might be easier to, act maliciously. Proof of stake blockchain networks use the amount of stake a user has as a determining factor for publishing new blocks. Thus, the likelihood of a blockchain network user publishing a new block is tied to the ratio of their stake to the overall blockchain network amount of staked cryptocurrency. So the methods for how the blockchain network uses the stake can vary. There are many approaches like random selection of stake users, multi-round voting, coin aging systems, delegate systems. So in the coin aging systems, once you stake some coins, the age becomes zero, so it has to take some time so that later you can reuse them and so on. Regardless of the exact approach, users with more stake are more likely to publish new blocks. So this is somewhat, people don't like it because rich becomes richer in that scenario. So, Jesus wouldn't like it, in other words. So here's a little bit small table again from NIST, which compares the consensus models and shows you advantages and disadvantages. Proof of work has advantages because it is hard to do denial of service by flooding the network with bad blocks. Disadvantage is that it consumes a lot of electricity. And when we talk about Bitcoin and Ethereum, I will show you the estimated yearly electricity consumption. So, but currently we don't like it. Also, the hardware arms race is a problem because people are trying to build faster hardware, but keeping it to themselves so they can mine faster and so on. So it will be, another problem. For instance, in the Ethereum case, people are buying the new GPUs. So even gamers cannot find GPUs to buy. And due to the pandemic, we have the chip crisis. So, for instance, NVIDIA 3000 series were very hard to find due to this case. Also, there is a 51% attack. If you have the computational power, which is the 51% of the whole mining power, then you can, take over the blockchain. The advantage of proof of stake, especially with respect to the proof of work, is that it requires less computation, but by less computation, we mean negligible computation, actually. Compared to this electricity consumption, this is nothing. And stakeholders control the system. This is a good thing, but it is also a bad thing, because once the stakeholders control the system, it causes a possible centralized power, which is actually against the idea of Bitcoin, because there we wanted to have decentralization, we wanted to have democracy and so on, but now we might have a centralized power. And 51% attack now becomes possible not by computational power, but by enough financial power. If you have more stake, like 51% of the stakes, then you can take control of the system. These are used in permissionless systems, but for the permission system, we can use round robin. Less computation, easy to understand, but now we are actually giving the ability to create blocks to everybody. So we have to kind of trust these publishing nodes. For the proof of authority or identity, it is fast, dynamic block production, but provides a centralized point of failure, because the person you trust or the identity of might act maliciously. There is no guarantee. You can take legal action, but if it is between different countries, so international law might be very slow to solve your problem. Proof of elapsed time. Here you are actually using a special hardware designed for this scenario, or maybe you are using the trusted environment part of the CPU or something. So you rely on the hardware, but the disadvantage is that the hardware might be compromised, or hardware might actually be designed in a bad way. Most of the time, we always trust this trusted environment of the CPUs, but in the last 10 years, we observed many cases where it was very easy to perform side channel attacks. So this scenario sounds good, but in my opinion, is very hard to achieve in real life. Once you give the hardware to the users, they might somehow compromise the hardware. So ledger complex and resolutions. It is possible that multiple blocks published at approximately the same time. This can cause different versions of a blockchain to exist at any given moment. These must be resolved quickly to have consistency. This is what I mentioned a little bit before. Conflicts temporarily generate different versions of the blockchain. Conflicts are usually quickly resolved. Most blockchain networks will wait until the next block is published and use that chain as the official blockchain, thus adopting the longer blockchain. This is actually the main reason why you wait for 6 more blocks to be added to Bitcoin, so that you're sure that it is the official blockchain. Okay, but if you invested too much money, instead of waiting 6 blocks, maybe you wait 60 blocks. We will talk about it when we talk about Bitcoin. So another thing now is to talk about is forking. So this one, sometimes people talk about this as forks, but this is actually a conflict. So at the same time you create different versions of the blockchain, you very quickly resolve it. So it is not a fork. But there's another concept that we call forks. This is changes to a blockchain network protocol, and data structures are called forks, okay? A soft fork is a change to a blockchain implementation that is backwards compatible. So non-updated nodes can continue to transact with updated nodes. So this in the Bitcoin, we had many soft forks before. By many, I say, let's say maybe 4 or 5. SegWit update or the Taproot update are soft forks, which provided new abilities, modified some of the implementations. For instance, in the latest soft fork, which happened in 2021 November, Bitcoin obtained the algorithm Schnorr signatures. So this was just the addition of a cryptographic algorithm. So this is why it is called a soft fork, because non-updated nodes can still continue to transact with updated nodes, but they would not understand Schnorr signatures and so on. But a hard fork is a change to a blockchain implementation that is not backwards compatible. So at that point, you actually create 2 different blockchains. It is important to note that while most hard forks are intentional, software errors may produce unintentional hard forks. Generally, this happens when the blockchain supports smart contracts, and a software written for that blockchain might provide different results for the same smart contract. So this way you can unintentionally create hard forks. But intentional hard forks also happen. For instance, for Bitcoin, some people increased the block size from 1 megabyte to 8 megabytes, created a new cryptocurrency called Bitcoin Cash. With cryptocurrencies, if there is a hard fork and the blockchain splits, then users will have independent currency on both forks. So this is actually what happened with the Bitcoin Cash hard fork. So for instance, before that, assume that you have 10 Bitcoins. After this hard fork, you also have 10 Bitcoins, but also have 10 Bitcoin Cash, because your money is duplicated in both of the blockchains, right? If flaws are found in cryptographic technologies within a blockchain network, the only solution may be to create a hard fork depending on the significance of the flaw. So assume that we found a very easy way to find collisions for SHA-256, then all of the security of Bitcoin will be lost. So at that point, we have to create a hard fork by removing SHA-256 and maybe putting something new like SHA-3-256 and so on. So there may be hard forks in the future due to some flaws that we found. So I mentioned that smart contracts have to work exactly the same in different software and different platforms. So smart contracts extend and leverage blockchain technology. A smart contract is a collection of code and data that is deployed using cryptographically signed transactions on the blockchain network. The smart contract is executed by nodes within the blockchain network. All nodes that execute the smart contract must derive the same results from the execution, and the results of execution are recorded on the blockchain. In Ethereum, due to some software bug of some software, some smart contracts actually provided different results, so they had to roll back to this. A smart contract can perform calculations, store information, expose properties to reflect a publicly exposed state, and, if appropriate, automatically send funds to other accounts. Note that not every blockchain can run smart contracts. It depends on the scripting language that you use, actually. So let's again focus on limitations and misconceptions. People always talk about immutability of a blockchain, saying that nothing can be changed, but the correct terminology should be tamper evident and tamper resistant. This is important. So for instance, there can be competing chains, there might be conflicts. So at this point, you cannot say it is immutable because there are actually two copies, and maybe one transaction is included in one block and not in the other one. So you don't know which one will be the winner. So you don't know if your transaction will be included in the blockchain or not. There is always the possibility of 51% attack. Also, in these two examples for the permissionless case, but for the permissioned scenario, even if you trust those people, they might misconduct. They might have a misconduct, and they might tamper the blockchain. So it is not immutable because people can change it. But in that scenario, if you know the identity of these people, you can take some legal actions. And another limitation is beyond the digital or the oracle problem. Most of the time, we are trying to connect blockchain with the real world events, but you can never prove that something happened in the real world. Okay, so if you want to buy something, for instance, with Bitcoin, so you might create the transaction, but that people may not send you the product that you are trying to buy, right? So there is not an easy way to guarantee that something really happened in the physical world so that you perform the thing in the digital world. So this is always a limitation. Another thing, the misconception is the idea that there is no trust. Actually, there is trust because there is no trusted third party for certifying transactions, but there is still a great deal of trust in the cryptographic technologies used. In some cryptocurrencies, people use some wrong cryptographic algorithms and they were broken. We also have to trust in the correct and bug-free operation of smart contracts, which might have unintended loopholes and flaws. We have to trust in the developers of the software to produce software that is as bug-free as possible, which is a very hard thing to do, by the way. We also need to trust in most users of the blockchain are not colluding in secret. If a single group or individual can control more than 50% of all block creation power, it is possible to subvert a permissionless blockchain network. Even if you don't have the 50%, for example, you might have the 40%, and you can still perform this kind of 51% attacks, but the attack now does not work with probability 1, but probability something close to 1. So the 50% here is not a definite limit here. And finally, for blockchain network users not running a full node, there is trust that nodes are accepting and processing transactions fairly. So this is very important. Most of the time, people use wallets with their mobile phones. For instance, you're transferring Bitcoin or Ethereum. So you install a software, but recall that the Bitcoin blockchain currently is more than 390 gigabytes. You don't download that blockchain to your mobile phone. Similarly, Ethereum blockchain is more than 300 gigabytes. So you don't have the blockchain in your software. So your software actually trusts full nodes. So here you have to trust somebody else at the end. Okay. So with all of these misconceptions, now it is again to our famous slide, when you may need blockchain, because in the beginning there was a huge hype. People said that blockchain is the biggest invention since the invention of internet or so. They said a lot of fantastic things, but nothing happened in the last 10 years. We didn't see good examples of blockchains other than cryptocurrency. So people started to think that maybe you don't need a blockchain. So people started writing papers like why you don't need a blockchain and so on. So we created many questions and to check if you really need the blockchain. Thanks to USA Department of Homeland Security's Science and Technology, they provided a flow chart, which is very similar to the ones I created, but this is somewhat better because it also provides you the solutions. For instance, it started asking you, do you need a shared consistent data store? If your answer is no, then you should consider email or spreadsheets. If you say yes, then you move on. Does more than one entity need to contribute data? This is very important. Almost everybody who came to me, who wanted to use blockchain in their company, answered to this question as no. So I said that maybe you should just use a database, because otherwise this means that you are not trusting yourself and there's no solution for that. But of course, maybe there's only one entity contributing, but maybe the government want to, audit it or something like this. So if there's auditing, you can continue. Question is, data records once written are never updated or deleted. If you say no, consider using database. Sensitive identifiers will not be written to the data store. This is very important. A lot of people who wants to use blockchain claim scenarios where to use it, where they say that this is permissionless, everybody can read it, but they're also putting sensitive data to the blockchain. So this is not correct. So if your answer is no to this, you can use encrypted databases. Next question is, are the entities with right access having a hard time deciding who should be in control of the data store? If no, you can consider using managed database. And finally, do you want a tamper-proof log of all rights to the data store? If your answer is again no, you can still use the database. But if you say yes to all of this, then maybe you may have a useful blockchain use case. Okay, this is why we are not seeing many blockchains in the wild. Okay, thousands of papers are published. We can use blockchain to this and this and this, and nobody really deployed them because most of the time they don't really think about the real world scenario, because once you do it, you realize that all of those proposals does not answer these questions as yes, and you realize that you don't need a blockchain there. Most of the time, database is your solution, but also some people only use blockchain to have a distributed system, but people acting like idea of distributed systems are created by blockchain. But before that, we had distributed systems. For instance, torrent is a distributed file sharing system. So most of the time, many papers where they propose to use blockchain, actually, they can simply use torrent. So there are many, unfortunately, wrong papers in the wild. So you have to answer to these questions before thinking about the useful use case for a blockchain technology.